Okay, greetings. We are going to implement Leet code 162, find peak element. So you must find an element that is larger than its neighbors. So here we need to return the index at 3, which is 2. Here we need to return the index here or the index here, and that is index number 1 or index number 5. And we're supposed to do this in O log n of time, but in this video we'll just do linear time and then do a follow-up video for log n of time. So here we return index 2. I'll put a tick by the relevant element, and here we could return index at element 2 or the index at element 6, which would be, the index 1 or index 5. So, simple way to do this is we just loop through the array one element at a time and check if that element's value is greater than the previous value and the next value. So, loop through array one element at a time and check if that element is greater than both previous value and the next value. We need to think about what happens if the values are equal then to each other, but if we read the conditions, it turns out that no values are equal when they're next to each other. So that makes your logic a little easier. And also, the 0th element is considered larger than the negative first element, and the last element is considered larger than the imaginary element to the right of the last element. So we could do something like for I in range length of nums, and then say, okay, well, if the value at I, index I, is greater than the value at I minus 1, and the value at I is greater than the value at nums I plus 1, then we return I. But this quickly runs into some issues. One is, let's say we're at index 0, well, we're going to get out of bounds error. So we need to start off from the first index. But then there's also another issue as well. If this is an exclusive bound right here. So if we start at the last element right here and compare with the element after the last element, that'll also be an out of bounds index. So we'd have to do something like this. But now, what do we do about evaluating the first element? Well, we could do something, we could have a sort of special check at the start where, if nums of 0 is greater than nums of 1, we return 0. But then even here, nums might only be of length 1. So we need another special check for if length of nums is 0, return. Sorry, if length of nums is 1, return 0. Now, will we ever get an empty array? No, the array will be at least length 1. So this will get us the answer. But what if the answer is that for every single one of these scenarios here, the conditions failed? When would that happen? Well, that could happen if you're continually increasing the value. So here, nums of I is greater than nums I minus 1, but nums of I, well here, yeah, nums of I has always been greater than nums I minus 1, but nums of I is not greater than nums I plus 1. So if we're in this scenario and all of these failed, that'll mean we need to return the last element. So here we just return length of nums minus 1, which is the last index. So let's go ahead and trace through these values and see see if our algorithm works for these values. So we're gonna pass in nums for this right here, and we're gonna do this check right here. Length of nums is not 1, so we just kind of skip here. Likewise, 0 is not greater than 1, so we skip there. So we're gonna go set this range to be from 1 to 3, exclusive bound. And we're going to start off with I equaling 1. So is nums at 1 greater than num 0? It, in this scenario, is not, or no, it is, yeah. So this is true for the first part, and is nums at 1 greater than nums at 2? No, it's not. So now we set I equal to 2. So here, 3 is greater than 2, and 3 is greater than 1, so we do return true over here. So this seems to work for this scenario. It seems to be, no obvious errors. So let's see if this runs. Oh, never mind. We got an error. Unsupported operands times. Oh, yeah, we need a -1 here. Okay, now can we simplify this algorithm? Well, we can. And one way to do that is if we look at the numbers here, we're continually checking if nums of I is greater than nums I minus 1. But if you think about it, we've already done that comparison when we were looking at I minus 1, because when we were looking at I minus 1, we were checking if I minus 1's value was greater than I's value. So to be more explicit, we already checked this Boolean expression for the previous value I and found that it was false. So we found that the following was false, that nums of I minus 1 was greater than I, aka what we found was true is that nums of I is greater than nums I minus 1. So this Boolean expression will always be true by virtue of the fact that we have already visited this loop on I minus 1 before. So we can get rid of this expression here. And that does work for 0 and 1, because here what we found was false was that nums of I minus 1, which is 0, and nums of I, which is 1, was false. So the logic still holds even for this range. So if we run this again, this is still going to pass. Okay, but now we can think, well, the only reason we had this expression here was to avoid the out of bounds by 1 error. So we could get rid of this expression and start a range at 0. And that's the default first parameter anyway. So we can get rid of this and simplify this, even more. So this should also work. But now, do we even need this right here? Well, if length of nums is 1, we return 0. Well, how would that translate to expression over here? Well, that would be for I in range from 0 to 1. That'd be actually I in range from 0 to 0, because we go length of nums is 1, 1 minus 1 is 0. So this doesn't even get evaluated at all, so we automatically just would return the length of nums, which is 1 minus 1, which is 0. So we can get rid of this expression as well. And the next video we'll do the O log of n solution. So technically here we're visiting every element once until we find the solution. So worst case scenario is O of n, and I guess you could assume, well, the average case scenario depends on your data distribution.